Hello everyone, this is the third video in the tutorial series about how to use the FitMulticell pipeline. In this video we will try to run a live example in order to show and explain different aspects of the FitMulticell pipeline. The example that we want to execute today is already existing in the FitMulticell repository in the GitLab. You can see the example here, so if you went to the GitLab repository of the FitMulticell project, go to the doc folder. Inside the doc folder, go to the example folder, and here is the example that we will execute today. It's called demo cell motility, and in order to run the example you need also to have the XML model for the cell motility also. So you can check the example here and you can install the model from here. Let's go back to our Python script. This code is similar to what we have on the Jupyter Notebook example on the repository. The first step that we will import PyABC package for the parameter inference. Also we will import the FitMulticell package, and we will import several other packages that we would use in this example. The first step that we will locate the path to the model that we just downloaded from the repository, and the model will have XML format. And the second argument that we need to define is the parameter map or par map. The parameter map is a dictionary. The key for this dictionary is the parameter name or the parameter ID that you want to fit. For example, here we have two parameters, motion strength and the noise level, and the value for this key would be the XPath for the parameter that we want to fit on the XML model. After that we will call the model module from the FitMulticell package, and we will call the function Morpheus model, and this takes several arguments. The first one is the file path to the XML model. The second one is the parameter map, and the third one, which is an optional one, is the executable file for Morpheus. So if your Morpheus is not on the default path, then you need to define the executable here, and several other arguments. If you want to know more about this argument, you can check the code here. Go to our repository and then go to FitMulticell, go to the model module, and then in the base file you can see a description of all arguments that you can define for the model modules. Let's go back. The next thing that we define here is the true parameter value for the parameter that we want to define. So for the parameter value, we already know that the true parameter value is 1, and for the second parameter it's 0.1, and we will use that just to check whether or not the parameter fitting result is as expected or not. And then we will define a limit for this parameter, and the limit would be multiplying the true parameter value by 0.1 for the lower limit and by 10 for the upper limit for the two parameters. So for the first parameter we will have a limit of 0.1, and then the upper limit would be 10. For the second parameter, the lower limit would be 0.01 and the upper limit would be 1. The second step, which is this section here, is where we define our measurement data. We will use the measurement data to compare between the simulated and this data, and in order to see how good is our fitting, how good is our parameter value in explaining the simulated data that is similar or not similar to what we have on the measurement data. And then we will define the distribution for the different parameters in this section here, and for all the parameters that we want to define, we will use a uniform distribution between the upper and lower bound that we define in the limit dictionary. And then here in this section we will define our distance function. In this example we use two distance function, and then in the next step we will aggregate the result of the two functions, and the result would be here in the distance variable. The next step, we will define a new object of the ABC SMC class, and this object will have the model that we defined above, the prior distribution for all the parameters, the distance function, and some optional arguments such as the population size. Here are a list of some of the optional arguments also, such as you can define the summary statistics, you can define the transition function, you can define the epsilon, the sampler, and so on. The next step, we want to create a new database to store all the fitting results on it, so we can retrieve these results later. Here we will define the path and the name for the database. In this example, we will save it on the temp file, and we will give it a name of test.db. The next step, we will create a new object of the history class, and this history object will take that database path and also the measurement data that we define here in order to compare the simulated result to. And here in this line, we will start running the fitting process, and this abc.run take the stopping criteria as an argument, so you can define, for example, the maximum number of population that you want to have. Here are also some additional optional arguments. For example, you can stop when you reach to a specific minimum epsilon or minimum acceptance rate, and so on. And finally, we will obtain some plots in order to see how good is our fitting of the parameter of interest. From the PyABC package, we will call some visualization routines, such as, for example, plot the epsilons for different populations, and also we want to plot the KDE matrix. So let's run the code now. As you can see, we have started the fitting process. It will tell you at the beginning how many cores it will use to parallelize the fitting process, and then we will start the fitting process. You will know the ID of your fitting, so later in the database you can check the fitting of this run using this ID. You can see the starting time of the fitting, the end time. Here is still none because we are not finished yet. And then you will see the fitting details for the different population T. For example, at population T0, we started with this epsilon, and then as we go further in our population, our epsilon is getting decreased and decreased, because now as we go further in our fitting, the distance between the measurement and the simulated data get shorter and shorter. Now, as you can see here, at each population we have 20 accepted particles because we have set the population size to be 20, and we will stop when we reach to the maximum number of population of 7. Now let's plot the result, and let's run again the fitting process. Again, as you can see, different details at each population T. You will see the epsilon, the number of accepted particles, the total number of particles that has been evaluated, and information such as the effective sample size for each population. If we reach to population 7, we will stop. And here is the posterior distribution for the two parameters of interest, the motion strength parameter and the noise level parameter. here is 1D output of the posterior distribution of the different parameter for the noise strength here, and here for the motion strength, and here for the noise level. And in the orange dash line you can see the true parameter that we set before. Also you will have a figure that show you the 2D of the posterior distribution for the two parameters. And this is the epsilon value across different population index from 0 to 6, as we requested here to plot this epsilon. So as we can see that we started with epsilon around 30,000, and then at the end our epsilon was below 5,000, and as we will increase the number of populations as we are expecting the epsilon value to decrease. There are more visual routine that can help you in understanding understanding your fitting process. You can see all the visualization routine from PyABC side and from the FitMulticell side in the different repository. I will leave the links for the PyABC and FitMulticell, and also for Morpheus, all the repository for the different tools in the description of this video. And this will conclude our video today. Thank you for watching, and see you in the next video.